Howdy there, everybody. In this video, we're going to learn some more about nuclear decay, specifically how fast a nuclear decay occurs. We want to be able to describe the rate of a nuclear decay. So here are the things that we should be able to do so far. Number one, predict the products of a nuclear decay. And then number two, calculate how much energy is created from the mass defect during a nuclear decay process. So again, our goal today is to be able to describe how long it takes something to decay. Like, what is the rate of decay and how does it work? So let's consider as a hypothetical example a sample of a radioactive element that has 100 atoms to begin with. And then we'll use something called a Geiger counter to measure how often an atom decays. So we can measure the decay product. For instance, if it's alpha decay, we can measure when a helium nucleus is released. And from that, we can kind of get an idea of what's happening. So again, this is a hypothetical situation. I've got the data collected for you. And so I'm going to create a table with three columns. One being the time in minutes that's passed. The middle column being the number of decays I count during each minute. And then the right-hand column being the number of atoms left in the sample. So for instance, at time t equals 0, I have 100 atoms, because nothing has decayed. After 1 minute, using my Geiger counter, I measure that there have been 29 decay events, meaning 29 of those atoms have decayed into something else and released 29 alpha particles, for example. That means there's 71 undecayed atoms remaining in my sample. After another minute, I measure fewer decays, like 21, meaning that there's 50 atoms left in the sample. If I let another minute go by, I measure 15 atoms to have decayed, which means there's 35 atoms left in the sample. After 4 minutes, I measure 10 decays. After 5 minutes, I measure 7 decays, so now I've got 18 atoms left. And then after 6 minutes, I measure 6 decays, and so there are 12 atoms remaining. So notice during each minute interval, the number of decays goes down because the number of atoms that could decay has gone down. If we kind of make a graph of that, if we call the number of atoms remaining N, and we graph that versus time, we would get a graph that looks something like this, which hopefully you can recognize as making like a curvy shape. This would be mathematically called an exponential decay. Depends on something of some number to the power of t. It may be confused with an inverse curve, but it's actually an exponential curve. So here's my graph with the best fit line plotted to it. I want you to notice a few things. Number one, notice that 2 minutes after we started this whole thing, that half our sample decayed. At t equals 2 minutes, we went from 100 atoms to 50 atoms. Notice that after 4 minutes, 2 more minutes have passed, we have the remaining number of atoms again. So at 4 seconds, we went from 50 undecayed atoms to 25 undecayed atoms. And so we would say that this particular element has a half-life of 2 minutes. It takes 2 minutes for exactly half of the remaining sample to decay. That's kind of a really useful way of describing radioactive decay in terms of its half-life. The way that you might symbolize half-life is with a T with a subscript 1/2. Best way to do it. And again, it's the time needed for half of a radioactive sample to decay. If we have a smaller half-life, then that means we have a quicker rate of decay. So things that have a small half-life are things that will decay faster. We cannot predict when any particular individual atom is going to decay. It's basically impossible to do that. It's completely random, and so all this is just based on statistics. It's not possible to predict when one particular atom will decay. We can have half-lives that vary from tiny fractions of a second to billions of years, and it depends just on the stability of the nucleus. To give you a couple of examples, the half-life of oxygen-15, radioactive isotope of oxygen, is only 122 seconds. So it means if you have a sample of oxygen, say 100 grams, after a little bit more than 2 minutes, half of that oxygen is going to have decayed into something else. By comparison, the half-life of uranium-235 is 7 times 10 to the 8th years. So you can see there's a big gap between those two. So these numbers can vary widely depending on the stability of the nucleus. Kind of getting a little bit more mathy with this whole thing, we can basically take our exponential graph that we saw a second ago, and we can kind of write an equation to match it. Like we can express the number of decayed atoms as a function of time t as an exponential equation. So that would look something like this, where n naught is the initial number of atoms, e is the natural number, approximately 2.718. Hopefully you learned a little bit about e in your math class. And then lambda here represents something called the decay constant. And then t in that equation is obviously for time. To relate the decay constant to the half-life, we can do something like this. We can say that the half-life is the natural log of 2 over lambda. We're not going to take the time to derive all this. We're just going to kind of use it and go. So a large decay constant relates to a shorter half-life. The bigger one gets, the smaller the other gets. And a shorter half-life means that the species is more active. Active is a fancy word we use to kind of describe how quickly a radioactive sample is decaying. So activity, again, the rate at which the sample decays. We can kind of express that as the number of decays per unit time. There's a couple units we can use to measure it. The first is the Curie, what we might use here in the United States of America. And a Curie is 3.7 times 10 to the 10th decays per second. That's based on the decay rate of radium, which Marie Curie discovered. Another unit, which is more common in the international system, is the becquerel. Remember, Becquerel was the guy that first discovered radiation. And a becquerel is defined as 1 decay per second. So in real life, you would typically use things like kilobecquerels, or megabecquerels, or gigabecquerels even. If you are talking about radiation absorbed by a person, like for instance somebody that works in a hospital, that's typically measured in a unit called rads. I'm not really sure why a rad has the name that it has. So if you've been to a hospital, you may see people wearing something that looks like this. That's basically a radiation badge that measures how much radiation the person is exposed to. And that's measured in rads. So for example, if you're going to become an X-ray technician, you may have to wear something like this just to monitor the exposure to radiation that you receive. Typically, a little bit of exposure to radiation is perfectly harmless, but if there's some sort of malfunction in a piece of equipment, you want to know from the radiation badge before you find out due to being sick or something like that. So let's look at a real quick example. Sodium-25. We're going to use it in an experiment, but in order to get it from the reactor to the lab we're using it in, it takes us 3 minutes to get it down there. We start with a 5 milligram piece of sodium. The half-life of sodium is 60 seconds. The question is how much sodium is left over after 3 minutes. I'm going to show you 2 ways to approach this situation. The intuitive way and the mathy way. Intuitively, I can state that 3 minutes is 3 half-lives for sodium. That means that the sodium is going to be divided in half 3 times. And so after 1 minute, half of my original sample will have decayed, meaning I've got 2.5 milligrams remaining. After 2 minutes, another half of the sample has decayed. So half of 2.5 is 1.25 milligrams remaining. And then after 3 minutes, I've got half of 1.25 remaining, which is 0.025 milligrams. So after 3 half-lives have passed, I've got 0.625 milligrams of sodium 25 remaining. So that's relatively straightforward. We can do things like create a table to kind of keep track of these things as time progresses. Now, the little more mathy way to do it is to use the decay equation. So since I know the half-life is related to the decay constant, I can use that equation to calculate lambda, the decay constant. And so I just do natural log of 2 over 60 seconds. Which, if you wanted to get a value for that number, would be something like that. And so if I plug in that for the decay constant, make sure that we take the 3 minutes of time and we get it in the same unit as our decay constant. So instead of 3, I need to use 180 seconds. That would give us a number something like that. Notice that it's pretty close to the number we got before, but not exactly the same. The reason that it's not exactly the same is because we rounded off that natural log 2 over 60 thing. So if I kind of write it more like that, where I just keep it as natural log of 2 over 60, when I plug it into my calculator, I get the exact same answer that we got before. So even though I kept my decay constant out to 1, 2, 3, 4, 5, 6, 7, 8 decimal places, I still get a little bit of rounding error in my final answer due to that whole e to the power of thing. So if you're using things like this, when you get the decay constant, it's better just to leave it as the natural log of 2 over t when you plug it into the equation. So it kind of showed you 2 ways of approaching a problem like that. So here's our next time question. Question is, what is more dangerous to you as a person, being near a radioactive element with a short half-life, or being next to one with a long half-life? So kind of the question to think about and ponder, maybe even jot down something about your pondering, and we'll discuss a little bit more in class. Till next time, ta-ta.